Welcome, my friends! In this video, we will discuss how to determine an appropriate sample size for confidence intervals of the population mean and population proportion. Recall that the margin of error for confidence intervals is the distance from the point estimate to either the upper or lower bound of the confidence interval. For example, in a confidence interval for the population mean mu, the point estimate is the sample mean x bar, and a confidence interval might range from 95 to 105, centered around the sample mean of 100. The margin of error is the distance from the point estimate to either of the bounds of the confidence interval, in this case, 5. Generally, we prefer the margin of error to be smaller, as it allows us to be more precise with our conclusions. One way to decrease the margin of error is to increase the sample size. If a researcher knows how large they would like their margin of error to be, they can calculate the sample size with the formulas we will be showing in this video. Let's begin with the sample size formula for population mean confidence intervals. The formula to find the sample size is z times sigma divided by e, all squared, where n is the sample size, z is the positive z-score corresponding to the level of confidence, sigma is the population standard deviation, and capital E is the maximum margin of error. Now, the hardest part to get in real life is the population standard deviation sigma. Actually, typically this number is impossible or extremely difficult to find because it requires you to know the population mean and every observation in the population. So, often the sample standard deviation S is substituted in place of sigma in this formula, as long as the sample size used to find S is at least 30. Now you might be saying, hold on, Luke. I'm trying to calculate my sample size, so I haven't even taken a sample yet. How could I have a sample standard deviation? Good point. That's what makes estimating sample size so difficult. Either you need to get some estimate of the standard deviation from a previous study, or you might need to calculate the standard deviation once you have gathered a little bit of your data. For the simplicity of my examples, I will assume the population standard deviation is known, but just know that it isn't really that realistic of an assumption. Alright, let's look at an example. Brittany is curious about the mean price of all textbooks sold by Brian's Books. She would like to construct a 99% confidence interval about the population mean with a maximum margin of error of $10. If the population standard deviation is known to be $40, how many book prices should she inspect? Here is the formula for the sample size of a population mean confidence interval. The confidence level in our example is 99%, the maximum error is $10, and the population standard deviation, sigma, is 40. The only number we are missing is the z-score, which corresponds to the 99% confidence level. You may remember this table that I provided in a previous video with z-scores for common levels of confidence. If you want to know how to calculate these values with a table or TI-84 calculator, check out my videos in the description. The z-score related to 99% confidence is 2.576. Plugging into the formula, we have n equals 2.576 times 40 divided by 10 all squared. When you do the math, you get about 106.17. Now, since you can't sample a partial textbook, we need to round this value. But the key is to always round the answer up, unless it's a whole number. This ensures that we are within the specified margin of error. So rounding up, we get 107. Brittany should inspect at least 107 books for the margin of error in her confidence interval to be below $10. There are actually two sample size formulas for population proportion confidence intervals. The first formula is n equals p hat times q hat times z over e squared, if you have a preliminary estimate for p. And the second formula is 0.25 times z over e squared, if you do not have a preliminary estimate for p. A preliminary estimate for p just means some estimate of what p should be before the study even takes place. Sometimes this can be estimated from past studies, and other times it will be completely unknown, requiring us to use the second formula. You might notice if you plug in p hat and q hat equals 0.5 into the first formula, you get the second formula. 0.5 times 0.5 equals 0.25. So really the first formula becomes the second formula when we don't know p hat or q hat, and assume they are both 0.5, which happens to be the most conservative estimate. N is the sample size, p hat represents the preliminary estimate for the population proportion, q hat is the complement of p hat, or 1 minus p hat, z is the positive z-score corresponding with the desired level of confidence, and e is the maximum margin of error. Now, many textbooks actually show this formula with p and q instead of p hat and q hat, but in reality we will not know the population parameters p and q. Whatever values we are plugging into the formula will be some sort of estimate and not the true population value, so p hat and q hat are more appropriate than p and q. Let's take a look at an example. Alfred is trying to construct a 90% confidence interval for the percentage of people aged 40 and older that own a cell phone. If he wants a maximum error of 4%, calculate the minimum sample size required, assuming a preliminary estimate for p is 0.92 based on a previous study. The formula we use is n equals p hat times q hat times z over e squared, as we have a preliminary estimate for p. P hat is the preliminary estimate of 0.92. Q hat is 1 minus p hat, which is 0.08. The confidence level is 90%. The z-score is the positive z-score corresponding to a 90% confidence level, which we know from my handy table is 1.645. E is the maximum margin of error of 4%, or 0.04. Plugging into the formula, we get 0.92 times 0.08 times 1.645 divided by 0.04 squared, which comes to about 124.48. Again, since we can't sample a partial person, we round up to the nearest number, in this case 125. Alfred should survey at least 125 adults aged 40 and older in order for the margin of error in his confidence interval to be below 4%. Now, how would this process change if there were no preliminary estimate for p? That means we wouldn't have p hat or q hat. Well, then we would be using this formula, n equals 0.25 times z over e squared, which we introduced earlier and should be used when there is not a preliminary estimate for p. We already have all of the numbers that we need, so we can plug into the formula. We have 0.25 times 1.645 divided by 0.04 squared, which equals about 422.82, and rounding up gives us 423. Alfred should survey at least 423 adults aged 40 and older in order for the margin of error in his confidence interval to be below 4%. Wow, that number is a lot bigger than the 125 required sample size when we had a preliminary estimate. Intuitively, if we don't have a preliminary estimate for p, that means we have less information about our population, and will therefore need a higher sample size than if we did have a preliminary estimate. So therefore, when we lack a preliminary estimate, the required sample size will typically be larger, everything else equal. Alright, my friends, we have finished our discussion of sample size calculations for confidence intervals. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.